Uh, Good afternoon, everyone. This is Dr. Carlo Ng. Welcome to the Quantum Science and Computing webinar. I am one of the co-chair of the Quantum Computing Research Center at the Department of, I'm also associated with the Department of Bioinformatics and Medical Engineering, Asia University. This forum is organized by me as well as by Professor Huang and Mr. Alexson. The aim of this forum is to provide a platform for learning the basics and the latest development of quantum science and computing, a cutting-edge field that explores the power and potential of quantum physics for computation and information processing. We hope this forum is able to inspire and motivate you to pursue your curiosity and passion for quantum science and computing, and to equip you with the necessary skills and knowledge to understand and apply quantum science and computing concepts and techniques. We have a website for this forum. This is the URL address for this activity, https://quantum.asia.edu.tw. And once you follow this link, then this is what you see in the homepage. And click on this link. This will carry you forward to another homepage. In this page, please use this link to sign up for the talks we organize. In case you follow this link, then you are required to fill in the Google form to sign up. This is the cover page of this Google form. You just need to sign up once. No need to do it again. The system will keep your record in the database. And then on this homepage, there's another subheading that is call for presentation. We really like you to take a more active role in this event by voluntarily fill in a call for proposal found under this hyperlink over here. So you are very welcome to play a more active role in this quantum forum. All the talks are given for free. Right? And then we will evaluate your proposal, and then we'll get in touch with you to find out what is a good time for you to give the presentation. Now, subject to the speaker approval, we will send you the lecture notes and the link of the video recording, usually within 1 week after the presentation. But this is all subject to the speaker's approval. The speaker may agree or may not agree. Okay, so we respect the speaker's decision. Now, today, this is the second talk of our activities on quantum finance. Explore the fusions of quantum computing with finance. 2 weeks ago, we have Professor Guangguidong Humphrey from the Department of Economics and Finance. He's a professor at the City University of Hong Kong. Now, today, we also are very pleased to have Mrs. Xuan-Wei Wang. She's currently still a student at the Department of Applied Mathematics, National Yang Jiao Tong University, Taiwan. Xuan-Wei Wang is an undergraduate student in Department of Applied Mathematics, National Yang Jiao Tong University. She has with emphasis on the exploration of quantum computing and financial analysis domain. She received awards in a prestigious semester-long project competition. Now, in this seminar, Xu, the speaker, will elucidate the significance and primary challenges associated with the call option pricing problem. Specifically, Xuan-Wei delved into the intricate aspect of resolving high-dimensional Black-Scholes partial differential equations and outlined the fundamental structure of the algorithm. So for that, without any further delay, so let me pass my microphone to our speaker today. So,
Okay,
Xuan-Wei, so can you able to share your screen?
Okay,
Just a minute.
can you hear me right now?
Yes.
Okay, thanks for the professor. And let me share my screen. This one.
Yes. Okay.
Okay.
Yes. Everything looks good. The video, the audio, and the video are all running fine. Okay.
Okay,
Okay, you can start now.
Okay, thanks for the invitation from Professor Carlo Nu. And
Sure.
okay, and welcome to my presentation on utilizing quantum circuit for co-option pricing problem and unveiling quantum amplified estimation methods. And my name is Xuan-Wei, and my advisor is Professor Fang. We are from the Department of Applied Mathematics at National Yang Jiao Tong University. And this presentation is part of our quantum seminar series. So, okay. So the contents of the presentation today will include the introduction of quantum technology, contemporary, and the application of quantum computing. We will also touch upon the advancements of quantum computing in financial analysis, such as co-option pricing problem. And later, we will introduce some quantum simulation platforms online. Finally, we may sum up the presentation today and Q&A time. So the first section is about quantum technology overview. And for the quantum computer hardware, the common use of materials or methods are silicon-based spin quantum dots, ion trap, superconductor material, and NV centered. On the other hand, quantum computing has been used to solve some problems via physical properties to a single quantum dot, such as superposition and entanglement. So let's focus on the application of quantum computing. Like, for instance, the algorithm of QKD and QRNG here, QKD and QRNG. Quantum key distribution and quantum random number generators has changed the future standard of password encoding and decoding in cryptography. the file is so-called quantum cryptography, and the issue is called post-quantum cryptography. So you may scan the following QR code. The QR code is about the standard of post-quantum cryptography by the NIST in America. NIST means National Institute of Standard and Technology. It is a governmental authority in America. And that's all. Since quantum computing is conducted by simulating the physical properties as a quantum dot, so chemistry molecular simulation is one of the most important developments. And the algorithm named by variational quantum eigensolver, VQE. So for example, it can be used to calculate 1,000 combinations of molecular arrangements in a short time. So the QR code on the right here is the seminar about the use of VQE. It's a YouTube video. So after the quantum communication field and the chemistry simulation field, especially we talk about today is in financial field, and we can discuss more details here. So since the quantitative financial analysis is trading now, there are lots of risk analysis models to fit the real market, such as factor model, PCA, CBGN, or CAPN, and so on. And most of these models are ODE or PDE model, partial differential model, partial differential equations model. This means that the system is much more complex to solve. In addition, the thinner the time segmentation, the larger the amount of data. And moreover, since there is a limitation of the development about traditional hardware, computer hardware such as semiconductor right now by Moore's law. So for the bottleneck above, it will be we will believe that quantum system will be the vital role in the future because it can solve great amounts of data in the short time via his physical properties like superposition and entanglement. So you can tackle with the amount of data in a short time. Yeah. So here in this presentation, we will discuss the framework about how to solve call option pricing problem in this presentation. So first of all, let me introduce simply about the call option pricing problem. So what is call option? Call option is actually the contract for stocks or other assets that allows the buyer the right to buy assets at a specific strike price, and it also allows the buyer the right to conduct the trade or conduct the contract on or before an expired date here. And it also requires the responsibility of the seller to sell the assets at the strike price to the buyer. So the call option buyer predicts that the price of the assets will increase in the future so that he can buy the asset with relatively low price in the future. So the challenges lies in accurately pricing these options, so which is essential for the market stability. And the difference between call option and a normal, the traditional or normal, the common way of stock price is the difference is between the time factor. So you can see after this, you can see the formula for call option pricing is about the time and the payoff and the probability distribution for the stock price. So here is one of the most famous model in financial, trying to describe the call option market. It is so-called the Black-Scholes models. So the BS model simplifies the pricing of options using the assumptions like no dividends or no arbitrage. And the BS model is kind of solve the European option. It means that the call option is trading only on the expired date, and there is no limitation for buying and selling options. And the most important thing is that it calculates the option price based on the stock price behavior, and the stock price behavior is modeled by geometric Brownian motion with log normal distribution. So these are the important assumptions for the BS model. Hence, here is the geometric Brownian motion for simulating the stock price, DSIT, and the following is the natural log return, DRIT, which is generating from Ito's formula here. Let me let me say something. With the consideration of the presentation time today, so I will skip most of these details here. And if you have any questions, no worries, because if you have any questions, you can ask me in the QA time, or we can discuss later. Okay, so I will skip most of the details here. So from the simulation of stock price, we can generate the joint probability density function for the multiple portfolio. The variable ytxt is all about the strike price x at the time t to the strike price y in the future time, capital T. And here, we denote that the capital sigma here is about the covariance matrix C, covariance matrix C with time factor capital T minus T. Small t stands for the time right now. Okay. So here we can also generate the payoff function by selecting the best trading strategy. And thus, the option pricing UTX can be written in the exponential time factor times the entire integration. So the main integration is made up by the by multiplying the payoff function hy and the probability density function here. So once you solve the integration and times the exponential factor, then you can get the option price of the time t with the stock price x right now. Okay. So how about the quantum circuits on this BS model? So if you can notice that you can thought that the vital point is to solve the integration part here in BS model. So the common way or the traditional way to compute the integration is using Monte Carlo simulation. It is a typical way to solve the numerical integration. But in real world, right now, in real world right now, the computation is far too complex and thus decrease the computation efficiency. It means that since you have in real world, since you have the time, you may assume that the time is continuous. So the data is tremendous. The amount of data is tremendous. So you do the Monte Carlo simulation, you need more complex computation for the Monte Carlo simulation. Hence, Yang-Min Lee et al. In 2023 tried to build up the quantum circuits to compute it because quantum circuits can have the properties like entanglement or superposition. So it means that it can solve great amount of data in a short time. Yes, so they thought of this solution. So in this presentation, I will use Yang-Min Lee et al. Their papers to confine this concept. So we will note that we still know that with the consideration of presentation time, I will skip most of the details about the circuit here. Yes, but let me confide it again. No worries, because I can explain the details if there is much time after the presentation. So first of all, we build up the circuits for the PDF. We know that from the let from the slides before, we know that we need to solve the integration by multiplying the payoff function and PDF here. So this is our main question here, our main problem here. So we first build up the circuits for the probability density function, and that means we apply an capital P circuits to the most of the quantum bits, qubits. So the concept here is we operate the multiplier, this one, the square root of p qubit to each qubit, and sum the value of the qubit. So the square root of p qubit here is about the integration of probability density function, which denoted by PIN, and the sum of PIN has range 0 to 1. So it is a concept about the operation here. So once you conduct the operation, once you apply the operation to the qubits, then you can return the output as the probability density of the option price. Yeah. Second one, the concept of the quantum circuit for payoff function is like, first, to compute x plus b for all qubits, x plus b. We address that because we need to compute the value with qubits operation. So the symbol here, like the sum operator or the dot product operator, are written in a different way. But the concept is really the same, because you can see that you just sum up in the typical formula, you just sum up the x plus b. That means the affine function, yeah, x plus b, and you just sum up the value. And here, the concept is the same. You sum up you multiply the qubits, the states of qubits by the constant, and plus another constant b, and sum up the total value. So the concept here is the same, but but is written in the different ways. So okay. And second is to find the maximum value, like this one, maximum value. The maximum value stands for the best strategy. What is best strategy? That means the strategy that has the best return. Okay, so after generate HI, we applying Y rotation to the qubits. And finally, the circuit's capital RH, or we say the operator. The operator RH changes the stats of all the qubits, like following picture, like this. So it is a small question about how to measure the value of all qubits, how to read the outputs of the circuits. It is a small question. Yeah. So finally, we abbreviate the circuit operation capital A combination by the P capital B. Capital P is, stands for the operation for probability density function, and RH is stand for like a pair function. So this means that applying the operation A to the qubits, to all of the qubits one time, you need to apply the operation P first, and then extend your circuit by adding this this number of qubits here. And the number of here are related to the number of assets, in your portfolio, and the number of qubits you may use to express a real number. And the big N here refers to the total number of qubits and used when making quantum circuits of the payout function. And after extending the scale of the circuit, we then apply the operation RH to calculate the payoff function. Okay, but as I said before, after applying this operation, after construct these circuits and operating that, there is still a small question about how to measure and generate the output for the circuit. So to be frank, it is a question about how to read the output by the quantum circuit, because it is not it is not like the traditional computer that we can read the output simply, because in quantum system, the all of the real values in quantum system are described as the superposition states or the entangled states. That means all of the data are entangled to each other. So that means you cannot just measure one of the states, one of the state of the qubit. Then let me sorry if you once you measure the one of the qubits, then you change the whole system. I mean you change the result of whole system. Can you image that? It is hard to image that, but yeah, how to read and how to measure is the problem for all the algorithms. So this is a small question. But if once we know the how to solve the problem, after that we can generate the output of computational option price. So you got a number for the you got a value for the option price you have calculated before. And after that, we aim to shrink the gap, shrink the gap between the computational, or say the output price, and the real one. So we then rescale the output value via quantum amplitude estimation algorithm. For example, like QAE, MLQAE, or IQAE algorithms to shrink the gap between the output and the real one, the real world option price. Yeah. So in next session, we want to talk about the QA algorithms. QA algorithms. That means quantum amplitude estimation algorithm. What is that? It is the algorithm to solve the problem. That's the problem. The goal is about to find the target value for the problem. The problem can be like um, salesman problem, traveling salesman problem. If I understand, if I remember right, traveling salesman problem, or the typical numerical integration. That is a problem. So is the goal is about to find the target value for the problem. And these algorithms is formed by applying quantum Fourier transformation and the Grover's algorithm. And the entire operations, circuit operation looks like this. And this means that you, first of all, you apply this operation. Then it means that you apply the Fourier, quantum Fourier transformation to all of the qubits, and applying the Grover's operation, which means that you run through the whole Grover's algorithm to the whole qubit. And finally, you do another inverse of quantum Fourier transformation again to the whole circuit. So the operation looks like this. Okay, so what is the concept of QAE? Is in fact the concept of QAE is actually the main idea of Grover's algorithm. So here is the small video here. So you can see that the initial vector is S here, and we suppose S is the target vector. We suppose that S is the target vector for the we need, and the vector omega is the index for the correct vector. So our goal is to make S vector approaches to the omega vector. So as the video shown, we continuously amplified the angle theta of the target vector S by reflecting, and to make it closer to the correct answer omega. Like this one, and about 4 times reflecting, you got a closer value of S to the omega. And of course, the iteration time as the capital T here has limit. So finally, yeah, so finally it means that T has the value of pi over 4 times square root of n, capital N, and minus 1/2. So it is the limitation for the iteration time. iteration time means that you need to do how many times you need to do the reflecting so that the vector S is approaching the omega vector. Okay, so this is the concept of Grover's algorithm. It means um, to find the target value for the problem. And the Grover's algorithm is the the main concept, the main idea of QAE. So although QAE brings computational efficiency to find the targets to the problem, it requires too much circuit space to conduct the algorithm. That means because of the QFT, it means quantum Fourier transformation. Although it may increase the efficiency about the computation, but it requires a lot of quantum gates and qubits to conduct one time the QFT. So the space is, we say the space complexity is tremendous. So hence, there are innovative QAE algorithms without the use of QFT, like IQAE, MLQAE, QAES. For example, this is my this is my favorite one. I think MLQAE may be interesting because Suzuki et al. In 2020 used the maximum likelihood estimation to take a place of QFT in the QAE algorithm, which I don't know if you have heard maximum likelihood estimation before, because this is the traditional statistics way to estimate the distribution, the value of distribution. So it combines the quantum way and the traditional computer way together. And we will see some of the results of the experiments. Yeah, so you can see the efficiency about the MLQAE is not okay. It's the I mean that is the better one to choose, better algorithm to choose to solve the question. So MLQA is my most interesting one. Okay, so others like IQAE. IQAE is about the iterative QAE. It means that Greenco et al. In 2019 it means that to find the confidence interval for the range of theta. And to the confidence interval, they have two kinds of boundary methods, which is CP bound and CH bound. So, and others like QAES, which means QA simplified. It means that it's simulating the tossing. It simulates tossing a coin to generate the range of theta. The range of theta. It means that it is kind of like quantum quantum random number generator. Sorry, quantum random number generator. So it's kind of like the idea of that. Okay. So these are innovative QAES today. So for comparison, Greenco et al. In 2023 conducted the experiments to compare those algorithms with traditional Monte Carlo simulation, the blue line here. And the experiment is about to use the following algorithms like Monte Carlo, QAE, IQAE, MLQAE, and QAES algorithms to calculate an integration problem. So they do the numerical integration work, and the result shows that IQAE, the green line here, and the pink one, the MLQAE algorithm have the best performances, and the QAE, the red one here, is the worst. So as you see, the MLQAE, although it is combined, it is part of using traditional way to compute the integration, but it has the better accuracy than the QAES. The QAES is typically the all the quantum way to simulate the target value, because that means it tossing a coin. Yeah, tossing a coin is in the process of tossing a coin, and it means that it typically use all the quantum way to tossing a coin. Yeah, I can say that. So you can see MLQA and IQA have the better accuracy and efficiency to one single numerical integration. Then the next question is how to simulate the algorithms. So right now I will introduce some online platforms to conduct the experiment. So we simply highlight leading quantum computing platforms like Microsoft Azure System. It is a cloud service to let people conduct their quantum systems online. And Xanadu quantum platform is typically for the quantum neural networks. Yeah, and that's one. D-Wave. D-Wave for it is a quantum platform using quantum annealing technology to simulate the your problem, your system. And I know that there is a laboratory working with D-Wave in our school in NYCU, and you may consider that some of you may heard the platform called IBM Quantum Platform. Yeah, it is the convenient one platform to use before, but in the beginning of this year, 2024, and if I remember right, 2024, they make lots of changes about the code instructions. So if you construct a system before in the IBM Quantum, in this year, your system may not running as smoothly because the instructions has been changed, and some of the packages, and moreover, some of the free quantum simulators in IBM Quantum platform requires user fee right now, so it's kind of expensive way. So it is not that easy to use for me as a student. Okay, so these three platforms on the slide are the recommended new platforms to conduct the quantum system. Yeah. So finally, the conclusion and the future work. So in conclusion, quantum computing holds great potential for solving complex problems in finance such as pricing, option pricing. And our future work will focus on the optimizing quantum circuits and exploring innovative algorithms like QAE algorithms. Then, thanks for your patience today. And right now is the QA time, and I also provide my email and personal HackND pages here, like the QR code here. So if you have any questions after this presentation, we can discuss online. Thank you.
Okay, all right. Thank you, Xuan-Wei, for the nice presentation. Okay,
Okay.
it's time the Q&A time. Maybe I can pose a few questions first.
Okay.
The one I'd like to know is about the Black-Scholes model.
Oh.
Yes, I'm also a beginner in this in finance. Okay? Uh, Now, the Black-Scholes model, you try to model the geometric Brownian motion integral, right? Using Monte
Yeah,
Carlo
yeah, yeah.
simulation.
Uh,
Yes, this.
yes, this one.
Yeah, so the one you highlight in paint color, right?
Yeah, okay, okay.
Yes. Uh, so, uh, so I'd like to know uh, the, uh, the P is the joint probability distribution, is that right?
Yeah,
Okay, all right. So in here, so you need to keep track of the number of assets in this integration, is that right? Say, let's say you might have, say, 10 assets to model. So you need to
yeah,
have
yeah, yeah.
10 qubits.
Yeah, yeah, yeah. Okay. First of all, sorry.
It's okay.
Let
因为什么
me
fallen
instead of
了？
using Chinese. So sorry.
So,
The small d here means that the number of assets. So if you have 10 assets in a portfolio, so you can have d equals to 10. Okay.
okay,
So
all right.
professor, uh,
Yes, yes, okay.
so continue. So can,
So,
thank you.
but then you have to keep track of this historical assets pricing for this 10 stocks assets for a certain period of time, is that right?
Yes. And right now the periods of time, the period is requires the small periods, a small, yes.
Uh-huh. So
uh,
you mean this is more like the peers, or I mean, when you do the Monte Carlo simulation, you need to make some assumption about this probability distribution function. Is that right?
yes, yes,
That can be obtained by modeling, say, the past history or record of those the 10 assets.
yes, yes, we need to
Okay.
calculate the option price. And yeah, the probability density function is made up by the historical data of the assets. So yeah,
Oh,
yeah, of course you need the
oh,
historical data to form out the joint probability density function.
okay. So
Okay,
can you go back to the previous slide about the integration?
okay, this
Yes.
one.
Yes.
Okay,
So this small p is a this what you have to learn from the past history. The
yes.
small p. Okay. All right.
Uh,
Yes. And then
because yeah, yeah, yeah. Yes,
And then,
historical data. Yeah.
and then at the integral, you have it's just more details. Is about the symbol you use. You have a capital letter R, and then D, and then
Oh,
plus. So what does this denote?
okay. So the capital R is the set of real numbers. And you denote the complex. The complex space is like capital C, right? So
Yes,
the
yeah,
real number as real number sets,
yes,
real number space, you denote the capital R, and
yes.
the and the
D,
plus
yes,
in the right
yeah,
右下，sorry,
yeah. The right,
in
yeah,
the
right
right.
hand bottom. Yes.
Yeah, right hand button, sorry. Right hand button, the plus means that all of the sets in this R space, it means that all of the value is positive. And the D on the right top, the small d is what I mean that the number of the assets in the portfolio. So if you have 10 portfolio, 10 you have 10 assets for your portfolio, then the D equals to 10.
Oh,
So
okay.
the whole space, I mean the R D plus the space is collected the numbers that in your assets, the value of the yeah. Sorry. It is kind of like the factor. It is kind of like the factor, and the factor has 10. Has D. The small d has D. Element has D elements, and each element is positive real number.
Okay, I see.
Okay.
And
So
then what about the HY? That is the payoff function. So where
yes.
do we get this information?
Uh,
HY,
okay. So HY
the
means
payoff,
that
yeah.
yeah, this one, and mean that because for the option pricing right now, we need to do the prediction for the future time. So we
Yeah.
need to the Y presents the future time, the stock
Ah,
price for the future time. Also, okay. So you need a payoff function is kind of like the strategy you use, and uh, so the Y here is the X here, and it means that maybe you can for the portfolio you may have the different weights to the different elements, like uh you have an S sorry so you have let's simply say that you have a strategy for the trading. Okay, you have the strategy so that the strategy about is about how you put your how you put your like how you put your assets to the different kind of stock. So the maxima here and the AX plus B, it means that you have different strategy for each of the stock price, and you plus the coefficients here. So the entire HY here is the strategy for you predict the entire payoff to the portfolio in the future time. Do you understand what I mean? This like
a little bit, a little bit, because I'm not a finance person. But the
okay.
payoff, so the payoff function, You sum over from K from 1 to big K. So it has to be the same as same dimension as the number of X assets, small d, or not necessary?
Yes, it is the same. The D
big
here
K,
in the yeah,
big
so
K, yeah, big K is the same as a small d, say 10, okay, 10 assets.
okay, I mean that so the D here is it's not like the capital K here. Let me show you another screen. Sorry. Let me show you
That's
another.
okay, yes.
Okay. I show my entire screen. Can you read that?
Yes, yes.
Okay. Okay. So it's kind of like this. Let me take some examples about the pair function. So can you see that there is 4 examples? Like the second one here.
Yeah.
The second one here is about we have to every asset of the portfolio, like X here, the bold X here, and we can have the different weights, like W here, to the assets, and minus capital K, kappa, minus kappa. The kappa means the since I want to pay off, so the kappa means that the price you buy the ticket, you buy the stock.
Yeah.
The price you buy the stock, and so that the after in the future the price you predict that the price will increase. So the weight times the price in the future minus the price you buy the stock here. Stock right now is like in Chinese like 成本，对对的，就是你的那个收益减掉你的成本。所以so the entire for the strategy, I mean that the WX minus kappa is the strategy, and after this you choose the maxima strategy. It means that the strategy that has maximum value, so you pick that as a pair function. So
okay, I see.
okay, so the K here is not not simply the same as the D.
Oh, okay.
Small D here. So yeah.
I see.
Okay, thank you.
Yes. Okay. Let me ask one more question before
Okay.
passing. See if anyone. Okay. Now for the result you show, you said the MLQAE is perform much better, right, compared to the other quantum amplitude estimation algorithm. So,
Okay.
do you know how many qubits they use in that study?
Okay. Let me share my presentation before.
Yeah.
Let me presentation before. So can you see the slides?
Yes.
The PowerPoint. Yeah. Yes.
Right.
So here is the MLQAE. So that means that once you conduct the QAE without QFT, once you conduct that, and you use the maximum likelihood method to estimate your output value. So it is kind of that. So the time complexity is like square root of k over the big K over big N, and times the epsilon you choose. The N means that in this question, in the call option price, the N is equals to the sorry, I think that the uh, eh? Okay, so sorry. The capital N means that if in the call option pricing problem, the capital N is equal to the asset, and the capital K is about the uh, mm, let me that's a little weird. Sorry. The capital K, it means like in a typical MLQAE, it means that uh, the correct answer, the target value we need to find, and the N here, N here should be the sorry, I a little forget the meaning of that, but the time complexity is like this, and the typical QAE algorithm is like here for the searching problem, the uh, complexity is about the square root of capital N over t plus 1. So yeah, it means that MLQA has much more uh, efficiency than the typical QAE algorithm. So sorry. uh, is
It's
that
okay.
okay or
Yeah.
yeah,
Okay. All
sorry.
right.
Okay.
Okay. Okay. So let me ask the audience. Is there any question from the audience?
Hmm.
Yes. Looks like someone.
So let me ask a question.
Uh,
This is Humphrey. Can you hear me?
Okay. Yes. Yes.
Yeah. Going back to your the integral,
Oh.
this professor just asked you
Okay.
uh,
Okay.
the option pricing integral.
Yes. This one.
Yeah.
Okay.
I suppose, okay, you have like small x, small t being like x will be like a vector, collection of assets, right? Collection of asset prices. And
Yeah.
then small x, small t will be the initial condition. So what you see
Yes.
today, okay?
Yeah.
And then your small y is also a collection of prices in the futures, randomly,
Yeah.
right? And then big T will be the maturity date, okay? So I'm just curious. Uh, the way that you bring in your quantum, I think quantum circuit, uh, are you going to have like just like you start off from small t and then you're talking about what happens only at maturity, or do you involve what happens in between current time and maturity? So which means let's say like current time and maturity, you can have like let's say 1 month. So 1 month you subdivide into let's say many intervals. Do you consider that into account, or you simply your quantum circuit only create, I don't know how to make it, create cases or scenario for small y at that time. Okay, so it's just like, would that be one step from now to maturity, or you take into account many sub intervals? That's my question number one.
Oh, okay. 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 Typically we use the later you have explained for. It's like you need to sum up the many intervals in the historical data. So it is not a whole like a month. If you need to predict the values 1 month after. 1 month after. So the integral means that you need the instant, like instant data. So the instant data means that you need to solve the integration in a small period. The smaller the better. So
but your integral only take into account like you're summing over all possible y vector.
oh
Am I correct? And
uh
also, I just want to mention, like if you're talking about stochastic properties, okay,
yeah.
you start off from small x and small t today, and then if you don't have any kind of a restriction in between today and maturity, stochastic property just tell us doesn't really matter what happens in between. At the end of the day, you just really need to know what happens at the end. Okay, so why bother? Why bother with all these intervals? But I don't know whether your quantum circuit have already take that into account or not. But just
Mm,
like only if you have, let's say, like option pricing, only if you have, let's say, I have some, let's say, some barrier condition. So like knocks in, knocks out option, then you really need to take you really need to think about like what happens in between. Sometime one of my assets got knocked out. Okay, then that will really
oh,
skew the final result. But if you don't impose any, we call that intermediate condition regarding the underlying asset, then why for stochastic properties tell us you don't really need to care about that. You just need to know what
oh,
happens, how random are all the asset prices at the end. Uh, I'm not sure whether you have do this part like in a quantum circuit way. This is my question one. My question two is you mentioned quantum algorithm on simulation, right? Your
yeah.
QAE or whatever.
Yeah,
Uh,
yeah, yeah, yeah.
will that like when you apply quantum idea for simulation, do you still have the idea of seed, like random seed in your algorithm, or because like traditional Monte Carlo, you have a random number generator, and then that random number
Yeah,
generator only follow a seed number, okay?
yeah,
And
yeah.
seed number basically get a well-known problem if you try to subdivide your path in the multiple steps, your seed might not follow the normal way to how it grows. Then it might skew your randomness. But I don't know whether QAE also has this kind of like
Oh,
number involved, or there are a brand new way to look at what does it mean by random. Okay, can you have
oh
some
yeah, yeah,
because
yeah,
I don't know because most of the time you start off from probability density function, and then
yeah,
you have like quantum state. I suppose your quantum state really comes out from density function, and not quite the way that we think based on a random process. Okay, when we talk about Monte Carlo, we talk about random process, and then we create random process according
yes.
to a seed. But your quantum way, I'm not sure. Just curious. Okay. Uh, um, yeah. This is my question.
Okay, okay, okay. I thank you for your question. I mean, and that I have been down this semester program for a long time. So this question is quite a new question because I don't think I sorry I have not think about the question before. So yeah, that mean the QAE it must has the kernel number generator. Yeah. So but I have never thought what like what kind of their work like sorry in Chinese sorry 就是 can I use Chinese
Yeah, okay, fine, yeah.
OK， 好 ，Thank you。就是我之前在做这个简报的时候，就是还没有想到这个问题，对。但是它应该是要用一个就是 quantum number generator 去做，就像蒙地卡罗有他自己的那个，有他自己的去generate 那个 random number 的方法嘛。对 ，QA 应该也会有，但是我想一下啊。transformation， QA 应该会有，但是
这是我的 my question is this. I look at one of your plot that compare Monte Carlo and all others like quantum algorithm.
OK
I look at a number called number of sample, okay, and I see a tremendously big number, 10 to the power 16. So traditional way using a seed number won't go that far, okay, because a seed number is not quite random. It is what we call pseudo random. So it just like keep on looks like random for, let's say, you can think about that to be a long period, but not that long. Okay. So your number of sample 10 to the power 16 quite exceeding I think like current random number procedures might not go that far. Okay. So let me just rephrase my question. What is the benefit? Okay. Will that be like using a quantum way to price option? Will that be in terms of the benefit comes from you can do it much more faster, or you can do it much more accurate, or what? I'm getting confused because I look at your plot here. Originally, I thought it will be you're comparing time, but you're actually comparing error. How does it get improved in error? When you have like because the question is there, and then you just have a different way to create different random sample, and in terms of accuracy, it will go for I suppose if you get more accurate, then you need more sample, then you get more accurate. But somehow I don't quite follow. Why you want to use quantum algorithm to price option? In terms of speed, and then I can understand, but in terms of error, I don't know. I don't get a point.
So here the comparison by green code, that means the entire graph shows that the error and the number of examples. So yes, let me think about it.
Never mind. I just raised a question.
Doesn't
matter. I know this will be a very big question for you.
So sorry, but
没关系。
No. Thanks for your question. And I thought that it is not quite simple to understanding the advantage of the QAS just simply by the error. It is not quite understandable. So
can I say the original
way?
Original idea is to do that faster. Am I correct? Okay.
Do that faster. It means that you can you can tackle with great amounts of data in one time, because the quantum system has entanglement properties. Entanglement. So you can. So it means that you can simulation, or you can you can simulate the data simultaneously.
Okay. I see what you mean.
So the fast is means
maybe
that
I can provide some information. For my understanding, Monte Carlo generator should be generate outside of circuit, and then after generate and then just quantize it into qubit. So I don't think QAE can generate a simulation. Okay.
Oh, so
But however, I have an issue that maybe you are interested. For
okay.
your process, I think the result in your paper show you have to recalculate to calibrate to market data, right?
Yeah.
Maybe you can show in your previous page.
Previous page. This one?
Yeah, previous. That's a result in your process.
Result. Sorry.
You just.
Sorry. Which one? The results.
When you're doing phase estimation.
Phase estimation. You mean this PPT or PowerPoint?
Yes, in your PowerPoint. In your PowerPoint.
This one.
Not this one. Before I think after you show the formula into the circuit.
Oh, after you. Sorry. This one. After I show the formula. Or
Yeah,
like this.
Before this one, before this page.
Before this page. This one.
Yes. Okay.
Okay. Yes.
You
okay.
should then recalculate. My suggestion, maybe you can inverse the result, inverse the process.
Oh yeah.
First, and find the phase.
Okay.
And then do another pricing. So because we have many market data, and we can model the market data into qubit. Then if we can inverse the process, then we can find the phase.
Okay. Oh, thanks for your your comment. But the actually in fact the difficulty is about the current hardware is not quite allowed us to do such a tremendous framework here. So nowadays the estimation of our, let's say, experiment can only conduct a simple integration, like simple numerical integration. So this
You just need to choice model.
yeah, toy model.
Or just think a easy price, an easy price.
Yeah, it all easy price. Okay.
Yeah, then inverse
Maybe that will work.
process and find the phase, and then use this phase to recalculate the market, to price in a new option.
Okay. Thanks
This
for
is
your
such as the inverse, we call implied volatility process in our financial engineer.
Oh, okay.
We use market data to find the implied volatility by Black-Scholes model, and then use the implied volatility to recalculate pricing, to recalculate the option price.
Okay. Oh, okay. Maybe that will work if you yeah. So okay. I might have something to do in the future. So oh yeah. That's a good evidence. Thank you. And okay, thank you. Oh. Market data.
Okay, yes. Mhm.
Market data. Sorry, how can you spell the market data? The market market.
Market data.
Yeah.
You know market data. You can find the market data from the stock exchange center exchange.
Oh, market market. Okay,
Yeah,
sorry. Oh, sorry. Okay,
市场资料。
Yeah. I used to calculate the like this is the another topic. I once used the market data to calculate the like like a three-factor model, like market factor model, risk factor model before. So I know the
Yeah,
access.
you know, for in financial engineer, we have used market data to find implied volatility.
Yeah. I use the yahoo.com so to find the market data. So if
that's enough.
that's okay. That's enough. Okay. Thank you. Oh, thank you.
Yes, okay. Yeah, we have some specialists in here. We have a nice discussion. Okay, so let me ask the audience, are there any other questions? Okay, welcome, Dr. Humphrey Tong, our first speaker 2 weeks ago. Welcome back. Right.
Thank you. Yeah,
Hi,
Please.
Professor.
my pleasure here.
Yes. Okay. Are there any other questions from the audience? Okay, so if no, then let's thank Xuan-Wei, our speaker, again.
Thank you.
Okay, thank you for Professor Wu.
Okay, all right. Okay, thank you very much. And this presentation is over. And have a nice day. All right, everyone.
Okay, thank you
Bye-bye.
for your patience.
Sure. Okay, bye.
Thank you. Bye bye.